This conference will now be recorded.
This is Craig Roy here. Can everybody hear me all right? Or can a couple people hear me?
I can hear you.
I hear you.
I hear you.
Well, good. I think people will probably be trickling in here for a few minutes, but wanted to get started and thank you all for um, joining us in our unique webcasting of our meetings. So it's a different style, but it seemed to go very well last month in March and had good response. So kind of excited to do that again, and we'll be doing that again next month. Um, I think if you have not read our newsletter that went out, there's quite a lot of important information in there. So please be sure to take a look at that. If you don't have that, feel free to reach out to myself or anyone else that is on the board, Cheyenne or Sam or Tracy. We're more than happy to get that information to you. Some of the key points of what was there is right now all of our spring events, internal and external, have been canceled or have been transitioned to a online type environment due to the COVID-19 pandemic. So it's definitely a little more interesting trying to work through all this. I'm sure everyone has had their differences and changes of how their company and how their structure has operated. I want to thank you, everyone that has definitely donated to RP this year. We're very close to reaching our goal for the year, which was higher than last year's goal. So that is great, and we do appreciate that support. And a lot of those fundings, they actually do stay internal to our state. There are several Ashrae grants that have been gone through our state through UAA and UAF. So it's we appreciate that support, and we appreciate that you continue to support Ashrae society as well as locally. One other interesting thing that we have in our newsletter this month is a quiz. This was something that kind of came up as try to engage some participation. It's going through and looking at some questions and looking through old copies of our newsletters and looking for some questions. So I think there's some details in the newsletter about how you can participate, and the goal of that is we just want to get people to engage and stay connected with one another. And we're also giving away a $25 gift card to any business that you would like. So we're not restricting this to one company. We want to have this participate to all of our members across the state, as well as if they want to support a local business that they can't frequent right now because it's currently shut down, then we want to give them that flexibility. So we appreciate everyone jumping in and joining us in that exciting and fun little quiz that we've got put together. And one more date that I believe Tracy wanted to point out is that she had incorrectly written the day down in May for our meeting next month. It is the May 21st, not the 15th, as she had written in the present message. So just wanted to clarify that in case anyone was confused. So we continue to do the third Thursday of every month as our meeting date. And that one is going to be an interesting one. We've decided to, since we can't do a tour, we had intended on doing a tour of the Anchorage Museum, but that's not going to happen, unfortunately. So what we're going to do is put together a panel of a few local experts across our industry, and we're going to talk about how our industry as a whole, as well as locally, is responding and tackling this COVID pandemic in terms of filtration systems, of how to handle it medically, as well as what can we do in the future that can make our systems better able to handle viral infectious diseases. So that should be a pretty fun one, and we're looking forward to having that. There'll be some information coming out further as to where we can head with that. This month, we're going to be going over indoor agriculture. And I know everyone's mind first jumps to marijuana grow facilities, but this is not just limited to that. This can be used for any fruit or vegetable or other that you can grow indoors with a system. So this is applicable information across the whole. I know there's quite a few containerized systems that are set up across our state in remote communities that provide fruits and vegetables year round. So this is a great topic that just kind of keeps our mind focused on great sustainable measures that we can use to not rely upon the barge that comes up every couple of days or every couple of weeks for our fruits and vegetables, so we don't run out when it seems to happen as it has happened this past season. So Eric Sturm with Trane, he is based out of La Crosse, Wisconsin, and he's been with the Trane company for, I believe, 7 years. And he's been an applications engineer and support for customers alike. So his role is varied and vast, and he has quite a bit of product knowledge on specific topics, this being one of those topics. So with that, I'd like to thank him for being able to host and present on this information, and I'll turn it over to Eric now.
Thanks, Craig. Can you hear me okay?
Indeed, we can. Thank you.
Awesome. Yeah, thank you for the introduction. Good afternoon, everybody. My name is Eric Sturm, and I'm with Trane. And yeah, so we'll spend the rest of the hour talking about indoor agriculture. So a little bit about myself. Craig gave you a nice introduction. I'm with the applications engineering team at Trane, which is a great opportunity to learn about cool things that I get to choose. And so one of the things happened to be indoor agriculture a couple years ago. My manager had asked me to learn a little bit more about it, and so I've spent the past couple years learning as much as I can about it in support of it. I'm also active within Ashrae as well. I've done a lot of work locally within the chapter, and now I do regional work. Our region, we're based in Region 6. Region 6 is RMCR, so I represent our members on membership council. And so that's an awesome opportunity. So thank you everybody for your support of Ashrae. Thank you for your very generous support of research promotion. Congratulations on nearly reaching your goal. That's a wonderful accomplishment. And again, thank you for your support. So for today's program, I'd like to spend a little bit of time talking about an overview of indoor agriculture, talk a little bit about plant biology inside of the grow room, spend some time talking about load calculations, because growing plants inside of a building presents different conditions that are needed and different loads that need to be compensated for with our equipment. And then spend the rest of the program talking about common systems that are being used. So first I'll talk about an overview of indoor agriculture. So what's in a name? There are a lot of different names that are being used to describe what amounts to be the same thing. The ones that you can see on the screen in orange are the ones that I hear most often. Controlled environment agriculture, sometimes abbreviated as CEA, is a common name. State of California is using its energy standard, and they're going to start tackling this space in several years, and they're using CEH, or controlled environment horticulture. Indoor agriculture is the phrase that Ashrae typically used. And you also hear vertical farming used a lot, and vertical farming is a little bit more specific, but it relates to growing plants inside of structures. And what is indoor agriculture? Well, it's a technology-based approach to grow crops inside of some kind of structure, whether it's a building or a container, like a shipping container, to achieve optimal harvests. It allows the grower to specify their environment. So rather than being at the whim of nature, if you will, growers can specify temperature and humidity, carbon dioxide, lighting, irrigation, and fertilization. And it also allows a variety of crops to be grown, such as cannabis, cucumbers, hemp, herbs and lettuce and microgreens and tomatoes, and some fruits and other vegetables as well. In terms of crops, most people are looking either at profitability, which drives towards cannabis and hemp, because the amount of energy and time that's expended to produce a crop of cannabis or hemp is very profitable. Alternatively, they're also looking at cycles to grow a crop, and so that's where lettuces and microgreens make a lot of sense, because they can be grown very quickly and harvested very quickly, and then that space can be reused for the next crop. So why are people growing plants inside? One of the reasons is the controllable environment, which I just talked about. This allows growers to have predictable outcomes in terms of quality and quantity and the amount of product that's being grown. They also can attempt to have the very same type of crop with the very same properties be produced again and again and again, and so that improves the consistency of their crop. And as Craig talked about in the beginning when he was introducing me, he was talking about container farms. It allows local harvest. So crops can be grown inside of buildings or containers, and they can be done locally. So in your climate, in the winter, you wouldn't normally be able to grow a lettuce crop, but if you grow it inside of a building, then you can, and that can be harvested, and it doesn't take a lot of time to transport it from where it's being grown to where it's being consumed. And in fact, there are some restaurants and grocery stores that will actually install container farms in their parking lots or adjacent to their buildings. They'll grow the crops right next door, harvest them the same day that they're consumed. So that's the epitome of fresh. There are a number of farms that make efficiency claims in terms of the amount of crop that they're growing. So you can see on the screen, I wrote 130 to 350 times more produce per acre of land using 1% of the water. This is a claim, it's a combined claim made by two different indoor agriculture companies that was reported in an article in 2018. The companies are Aero Farms and Plenty, which are two American-based companies. And so they believe that they can grow more food more consistently using a lot less water. The water use part comes back to water reclamation. So all the water so the majority of the water that's put onto the crop in order to have the crop grow is then dehumidified out, or it's drained out and collected, cleaned, and reused. So where are they being grown? We're seeing a variety of different spaces being used. There's a lot of repurposed buildings that are being used, so old factories or old warehouses that are being purchased for low amounts of money and then being retrofitted in order to support indoor agriculture. For instance, there's an old factory in my city here, La Crosse, that used to make boots, rubber boots, and much of the factory is empty, and so there's a company that is taking one of the floors in the factory, and they're growing hemp plants for CBD oil production. There are other ones that are purpose-built, so the buildings are being built from scratch, they're new construction, and so everything is being purposely laid out and set up in order to support indoor agriculture. Both purpose-built and repurposed buildings may include growing rooms or chambers, which allow the crops to be isolated. So if they're growing different crops can be isolated from one another, or if a crop requires different conditions for its growing cycle, growing it in a chamber allows certain conditions to be met for a period of time, then the conditions to be altered for another period of time until the crop is ready to be harvested. Alternatively, some growers will move their crops from one chamber to another. So they'll start in one chamber with a certain set of conditions. The crop is usually on movable tables, or there's some kind of mechanism that allows them to be shifted around. And so they'll be moved from chamber to chamber or area to area, allowing different conditions. And then there are companies that just have large growing areas. And so they'll take a large building or a repurposed building, they'll install their growing system, which can include lights and air conditioning and areas for people to walk and service the crops. And it's just, as far as you can see, it's just a growing area for the crops that are being produced. There are a variety of ways that plants are being grown. In terms of irrigation, there are a lot of techniques. Hydroponics is a broad phrase that's being used to describe a variety of techniques in terms of how plants are being irrigated, how they're receiving the fertilizers that they use to deliver nutrients. Aquaponics is a subset of hydroponics in sort of a way. Aquaponics includes the use of raising fish, and so it's a cyclical growing type where the fish swim in water and the fish excrete waste. That waste is then converted into plant food, typically by one or several types of bacteria, and then that nutrient-rich water is then circulated into the plant system, and it feeds the plants. The fish are harvested, the plants are harvested, and so the water is reused, and so it's a cyclical system. Sometimes the plants are oriented on trays or tables. If they're in hydroponics and the roots are suspended in water, sometimes they're suspended in a solid medium that is irrigated throughout the day. And there are vertical farming systems. Some of them orient the plants in a horizontal way. So if you can imagine from floor to ceiling, trays of plants spaced out. So each set of plants has lights or may have light shining on it somehow to power the photosynthesis part of the plant. Or there are other vertical systems where the plant is actually growing out of a tower system sideways. Lights are there as well. So there's a variety of configurations that are being tested and tried and developed. It's a very exciting space. So let's take a little bit of time and learn a little bit about plants and what they need, and then that'll filter into our loads and our systems. So here's an image of a plant on the left side of your screen. You can see the top part, the part that's above ground is called the shoot, and the part that's below ground is called the root. The plant itself has several systems, the phloem and the xylem, which are like circulatory systems for the plants to transport waters and sugars and minerals and acids from one section of the plant to another section of the plant. And plants themselves need a variety of elements in order to grow. They need oxygen and carbon dioxide. The carbon dioxide is sourced through the leaves. Oxygen is often sourced through the root system. They need a lot of minerals and vitamins that are sourced through the root system, like potassium, manganese, and sulfur. And of course, they need water. And a lot of the water is actually going to be evaporated out of the plant. And I'll talk about that in a moment. But the water also makes up the bulk of the circulatory system. So when we talk about growing plants, or when you speak with a grower, they're probably going to use a term evapotranspiration, which is a combination of the words evaporation and transpiration. So evaporation is water movement from the soil and the plant surfaces to the surrounding air. So normal evaporation that we're accustomed to in the HVAC world, you have drops of water sitting on the soil or on the surface of the plant, and it evaporates, and that's just normal evaporation. Transpiration is the one that's a little bit is unique to plants and one that we might not be familiar with. So transpiration is the movement of water within the plant, so inside the plant, and eventual release from the stomata on the leaves. So what happens is the plant needs to circulate water and minerals from the root system up into the shoot, so the above ground structure of the plant. And it does that by evaporating water out of its leaf system through these tiny openings. And you can see that in the picture. There's a tiny little opening. Water vapor is escaping from this opening, and that creates a concentration of solutes within the leaf, drawing up additional water from the root system, therefore drawing up additional minerals and nutrients from the root system. And so this evaporation is a normal process for the plant, and its purpose is to transport things from the root to the shoot. But from an HVAC perspective, that presents something that's unique that we don't see with comfort cooling, and that's the presence of water vapor being produced within the space. And so, as you can imagine, that's going to create a latent load that needs to be considered. And because the plant is evaporating water, it's converting liquid water to water vapor, it also produces a small cooling effect as well. And so again, that's something that we'll need to account for when we're sizing and selecting systems. So this transpiration is an interesting thing, and it's not a static thing. You can see in this graph, this is a graph of barley. The researchers took a number of, they took 6 segments of barley, and they did some testing to see how transpiration is affected when the plant is exposed to light and when it's not exposed to light. So daytime and nighttime, if you will. And you can see, if you were to just draw an imaginary trend line in your head, you can see that the transpiration rate goes from whatever its peak level may be to a level that's not 0. It's closer to 0, but it's not 0. And so from this information and from specific crops, we know that when the lights are turned off, when the indoor lights are turned off, the plants continue to transpire. That is, they continue to add water vapor to the space, but they don't do it at the same rate as when the lights were turned on. So it's about 66 or 75% of reduction in transpiration. But it's important to remember that the plants, even though the lights are turned off, and the lights are used to power photosynthesis, the chemical reaction inside of the plants that allow it to grow, even though those lights are turned off, the plant is still adding water vapor to the space. And so knowing these things, we as designers, we need to take a step back and think about our loads a little bit differently compared to comfort cooling. So here's a comparison with comfort cooling. You can see on the left side comfort cooling, and on the right side indoor agriculture. When we talk about when we talk about operating modes for comfort cooling, we typically talk about occupied and unoccupied, and there's some others as well, but basically, do we have people there or don't we? With indoor agriculture, we consider when the lights are on, powering photosynthesis, and when the lights are turned off. And some people will call this daytime and nighttime. And in this particular instance, I've put them in quotation marks because daytime and nighttime may not actually follow the pattern of the sun and the season. In terms of lighting power densities, you can see that indoor agriculture lighting power densities are significantly higher than comfort cooling power densities. And the range is a lot higher as well. Comfort cooling power densities are typically regulated by standard or code. Indoor agriculture, in terms of standards and codes, standards don't exist yet. Some jurisdictions are working on codes. Some jurisdictions already have codes. 30 watts per square foot is about as low as you'll see with current LED technology. 80 watts per square foot would probably be with a different lighting technology that's less efficient, like a high pressure sodium type fixture. With the lighting and having those high energy consumptions, you can also imagine that there's a lot of heat output, less so for LED, but there's still a lot of sensible heat that's going to be added into the space because these lights are turned on, powering the plant's photosynthesis. From a space temperature set point perspective, indoor agriculture usually has a wider control than comfort cooling. Comfort cooling, we know most humans are satisfied between 70 and 75 degrees. We have a lot of research to show that. Indoor agriculture, it may be crop specific, and it may also be the type of or the crop cycle, what cycle the crop is in. It might be specific to that as well. So the range is a lot larger. On the slide I wrote 65 to 83 degrees. I think the maximum that I've actually encountered is about 80 degrees. Space humidity is very similar. We know humans perform the best between 50 and 60%. They're happiest. Plants can go a little bit higher. A lot of growers are concerned about high humidity and the risk of microbial growth on their crops. So 75% is a high area. And so this produces unique space sensible heat ratio, or SHR conditions. Within indoor agriculture, we typically have 2 operating realms, daytime and nighttime, And in the daytime realm, we have what I would consider to be a pretty steep SHR, 0.25 to 0.5, indicating that while there's a large sensible load, there's also a very large latent load from the plants. And at nighttime, when the lights are turned off, our SHR might go to 0, or on the slide I wrote 0 to 0.4, indicating that there's maybe no sensible load or very little sensible load, and yet a very large latent load, or still a large latent load from the plants. And in fact, here on the 0, you can see I wrote an asterisk because we actually see a situation where we see negative SHRs, which I'll show you in a moment. In terms of ventilation, we ventilate buildings according to Ashrae Standard 62.1 when people are inside, but for plants, plants don't require ventilation. They are consuming carbon dioxide, not oxygen like people. And so what actually happens is many growers will choose to increase the amount of carbon dioxide in their growing spaces because carbon dioxide is a component that the plant uses. The plant itself will separate the carbon dioxide molecule and strip the carbon off, and the carbon is used when the plant creates glucose to support its own growth. And we'll see rates of 1,500 parts per million where a separate carbon dioxide system is installed, increasing the rate of carbon dioxide in the space. So one of the things that a grower might say to you if you're having a conversation with him or her is they might say, I'd like a temperature of 75 degrees in my space, and I'd like to maintain a VPD of 0.9. VPD is another new term for a lot of folks within the air conditioning industry. And what it is it's either the vapor pressure difference or the vapor pressure deficit. And it's simply defined as the difference in vapor pressure between the leaf and the surrounding air. So we assume that the vapor pressure of the leaf is at saturation because the boundary layer surrounding the leaf is full of water vapor. And so its relative humidity is 100%, it's saturated. So if we look at an example where the grower says, I'd like 75 degrees dry bulb, and I'd like a 0.9 VPD, we can figure out what set points we would need. So in this example, here's 75 degrees on the psychrometric chart, which comes out to 2.96 kilopascals. And before I go any further, I should probably talk about the units. Vapor pressure can be measured in a variety of units, but in North America, it's common to discuss vapor pressure difference or vapor pressure deficit, VPD, in terms of kilopascals, which is why in this example, I'm mixing units between imperial units and SI units. So again, back to the example, 2.96 kilopascals at the leaf boundary layer. And if we add in a difference of 0.9, we find our control point, which is 2.06 kilopascals, which falls onto the 70% relative humidity line. So if the grower said, give me 75 degrees and a VPD of 0.9, we can use the psychrometric chart to figure out that the grower is asking for 75 degrees dry bulb and a 70% relative humidity set point. Earlier, I mentioned a negative SHR. Negative SHR can happen when the lights are turned off and the plants are adding a dehumidification load to the space, right? So the plants are adding water vapor to the space. And so to maintain the space humidity level, we would need to dehumidify the supply air in order to offset the latent load that the plants are adding to the space. But what also happens when they're converting liquid water to water vapor is the plant is cooling the space. So if there are no other sensible loads within the space, no sensible loads due to envelope or equipment or sunlight or artificial lighting or lighting fixtures, then the plants are cooling the space, which means that we need to also heat the supply air in order to maintain the space set points, both temperature and humidity. From an HVAC perspective, this presents a very unique situation because this doesn't happen in comfort cooling very often, where the supplier needs to be dehumidified and then heated beyond the space temperature in order to maintain set point and humidity. So in summary, when the lights are turned on, we have high sensible loads from lighting. We have high latent loads from the evapotranspiration of the plants, and we have sensible cooling from the plants themselves. And so that creates a situation where we need our HVAC equipment to provide sensible cooling and dehumidification. And when the lights are turned off, or it's the nighttime mode, we have no sensible load from the lighting. We have some latent load from the plant evapotranspiration, and we have some sensible cooling from the plant evaporation, which presents an opportunity for primarily dehumidification. In terms of computing the latent load, so determining how many BTUs of latent load there are a variety of methods available. One method is to compute the amount of water in, how much water is being added into the plant system, and subtract the amount of water that's coming out. And this is a very common thing that factors into some of the other examples as well. There is an outdoor agriculture system called Penman-Monteith, developed by two scientists some years ago, that is used to help farmers estimate how much irrigation water they need to apply to their crops, given the crop itself and their location on the earth, so latitude and longitude, and the date, so how much sun, which filters into how much sunlight the crop is receiving, along with wind speed. And so this equation has been adapted to support indoor agriculture, where we don't have to worry about latitude and longitude, and wind speeds are relatively constant. There are also rules of thumb, such as use a certain amount of gallons per square foot of canopy of plant per day. But when talking about rules of thumb, we have to be really careful, because these rules of thumb, the irrigation rates, can vary by irrigation techniques, whether the plants are whether they're being subjected to drip irrigation, or if they're seeing if their roots are being submerged within irrigation water. And we also need to be careful about the per square foot term, because it can be used to describe per square foot of building area or grow room area, or it could be area of canopy. And when thinking about vertical farms, where plants may be oriented on trays that are stacked on top of one another, the area of the canopy could be much larger than the area of the floor. So if you find yourself in a situation where you need to know how much water is being added into the system, and you're working with a rate per square foot, you might need to ask some clarifying questions to ensure that you understand the correct amount of water that's being applied to the system. So these methods can be used within spreadsheets to automate the calculations, and there are software programs out there as well that can compute the latent loads based upon irrigation. So there's a variety of tools available, and some tools have been adapted. And yeah. So let's look at an example. This is just a generic example. The area of the canopy is 1,000 square feet. We're going to add 125 gallons per day into the system. The lights are turned on for 16 hours per day, which is pretty common for a lot of crops. And so the lighting heat gain is computed to be 28,800 watts, which turns into 98,300 BTUs. And the room set point is 75 degrees, and the relative humidity is 70%. The same example that I showed you earlier. So the VPD is 0.9. There's no ventilation, and the carbon dioxide will be maintained at 1,200 parts per million. So in this example, the lighting load contributes a sensible load, 98,000 300 BTUs. The plants are adding a negative sensible load because they're cooling off the space as they evaporate water, and so that's estimated at 52,800 BTUs. The latent load from the plants, evapotranspiration, is 58,700 BTUs, and so you can see these are totaled on the last row of the table. And the loads can be recomputed when the lights are turned off. So remember, the lights are turned off, there's no sensible load, and once the plants reach something closer to steady state, we can estimate the evapotranspiration of the plants. So if we were to do some sizing calculations and say that in order to maintain the temperature and humidity in this space, we're going to supply a 2000 CFM unit. You can see here I took the space sensible heat equation, took the total sensible load, and calculated a new supply air temperature based upon a 2000 CFM unit. And so the supply air temperature is 54 degrees dry bulb. And I took the space latent equation and did the same thing to calculate the humidity ratio of the supply air at 2000 CFM in order to offset 58,700 BTUs. And so that humidity ratio is 48.6 grains per pound. If we look at that on a psychrometric chart, it might be easier to visualize. So here's our return air set point. That's our 75 degrees dry bulb, 70% relative humidity set point that the grower asked for. So we can draw a couple of lines from the humidity ratio and the supply air temperature at 54 degrees to figure out what temperature we need to supply at if we're going to send 2000 CFM into this space. Follow our cooling coil curve down and figure out what our off coil temperature is. So in this case, our cooling coil is going to be cooling down to about 50 degrees, which is actually a little bit too cold. If we were to send 2000 CFM of 50 degree air into the space, we'd overcool the space. The humidity ratio is good. It's 48.6 grains per pound. That's what we calculated. So we will need to do a little bit of reheat in order to supply the right amount of air at the right conditions in order to maintain temperature and humidity in the space. So in this case, it works out to be about 10 tons. I think it's actually like 9.8, but rounded up for 10 tons. And our reheat load during the daytime is 13.3 MBH. And this is something that's actually more common than you might think, where during the daytime mode, if you will, when the lights are turned on, we're still adding heat into the space by heating up the supply air. This is pretty common because this is a dehumidification application. This is all about removing the moisture from the plants, from the evapotranspiration. And so doing reheat, even during the daytime mode when the lights are turned on, is more common than you might think. If we go back and replot with our nighttime conditions, we can see what that looks like. With our nighttime condition, because we have a negative sensible load due to the plants cooling the space, our supply air temperature is actually 83.1 degrees. So we're actually going to heat the air up, and our latent load was a lot less, so we don't need to dehumidify the air as far. Before we were at 48.6 grains per pound, now we're at 76.9 grains per pound. So again, if we look at that on a psychrometric chart, here's our return air condition at 75 dry bulb, 70% relative humidity. And we need to supply at 76.9 grains per pound with a supply air temperature of 83.1 degrees, which means we need to cool and dehumidify the air down to about 63 or 64 degrees so that it's the right humidity ratio, then reheat it all the way up to 83.1 degrees. So this represents a cooling load of about 3.9 tons and a reheat load of about 43.6 MBH. And again, this is very common during the nighttime when there's little or no sensible load in the space except for the plants, and the plants themselves are providing a cooling load. But we still have some dehumidification. So this is a very common thing that occurs. So in summary, we did a constant volume 2000 CFM unit. It's going to be a cool reheat configuration so that we can dehumidify the air and then reheat it to the right temperature. In the daytime mode, when the lights are on, we need 10 tons of capacity. The system cools down to 48.6 grains per pound, reheats at 13.3 MBH, so we supply at 54 degrees. And in the nighttime mode, we need 3.9 tons of cooling, so we only need to cool down to 63 degrees Fahrenheit, or a leaving air humidity ratio of 76.9 grains per pound. We need to apply a lot more reheat, 3 times as much more reheat, 40 to 43.6 MBH, meaning that our supplier temperature is a lot warmer. It's warmer than the space control set point of 83 degrees. So let's talk about common systems that are in use in order to do this. The first system that we see a lot of is conventional DX systems. They could be packaged rooftops or split systems, or even VRF units, and paired with dehumidifiers. So in this case, we've got a standalone dehumidifier. It may be installed in the room. Sometimes they're on the floor. Sometimes they're mounted to the ceiling or the walls. And there might be multiple dehumidifiers. They're controlled to a relative humidity set point, and they cycle on and off in order to maintain relative humidity of the return air condition. The conventional package DX unit has a zone sensor or temperature sensor in the space, and it operates in order to maintain space set point. These two systems work together in some cases. In some cases, they work opposed to one another. From an advantage perspective, they're fast to install. Both types of equipment are relatively easy to get and install. They have controls, very simple controls, and they're easy to service. Parts are easily found in most cases, so it's a very simple system. But in terms of drawback, you might consider this to be a precision cooling system or a precision dehumidification system, and a package rooftop with in-space dehumidifiers, not really that, because it's difficult to maintain precise space temperature and humidity. It can be difficult to operate outdoor equipment in cold weather. In my picture, I drew a package rooftop that was installed outside. In cold ambient conditions, those are difficult to operate because they need to operate in the cooling mode. They're cooling and dehumidifying in a lot of cases. Compared to other alternatives, typically they have higher energy use, and there's limited controls integration. If I back up just a moment, I should say that because there's no ventilation in these systems, there's hardly ever any air side economizing. There's several reasons why growers choose not to do air side economizing. One of them is they don't want to introduce any foreign contaminants through air side economizing, and another reason, and perhaps the primary reason, is if they're adding carbon dioxide into the space, air side economizing would dilute that carbon dioxide, therefore they'd be wasting their money. So many choose not to do any air side economizing. The next class of equipment is a purpose-built package unit or a split system. This could be a rooftop unit, could be a split system, could be a VRF system. In this case, we're going to have something that has some sort of dehumidification control. In my example that you can see on the screen, I've got a cool and reheating system. You can see the return air passes through a cooling coil, so it's dehumidified to the right humidity ratio, and then it's reheated to the right supply air temperature so that the space is being maintained. And in this case, it's a split system, so the condenser is placed somewhere outside, allowing us to reject the heat. In terms of advantages, it's an integrated system, so it has operating modes that don't oppose one another. With the the last one, where we're pairing rooftops with dehumidifiers, there are times that the dehumidifier, if it's not a split system, and most aren't, the dehumidifier is adding heating load into the space because the dehumidifier is a small refrigeration cycle. So there's heat from compression and heat from the condenser of the dehumidifier. So it's actually adding heat to the space, which would need to be accounted for in a load design. In this case, the unit is one unit instead of 2 units. It's not working to oppose one another. So we don't have to worry about that. We do have package controls available on a lot of these types of equipment. They're easy to install and service. Parts are readily found, and they're more efficient than conventional DX units paired with dehumidifiers. In terms of drawbacks, again, if you have components that are installed outside in the cold weather, operation can be challenging. Energy use can be higher than other options as well. The installed cost and the first cost of the equipment may be higher than the previous option of a conventional DX system paired with dehumidifiers. And spaces that have a negative SHR, like I was talking about before, may require a supplemental or auxiliary heating system beyond what the dehumidification package unit could do. So that dehumidification unit might use hot gas reheat to recover heat from the condenser in order to provide heating for the supply air, but that may not be enough. So another heating system, whether it's electricity or natural gas, may need to be provided as well. Another option are air handling units, which can be installed indoors and outdoors. They could be chilled water, or they could have a DX coil, or they could have a variable refrigerant flow system. Air handlers allow us to install different types of air-to-air heat recovery technologies. On the screen, you can see I've drawn a fixed plate heat exchanger in the series configuration, or sometimes called a wraparound configuration. There are options for desiccant wheels that improve dehumidification performance. So there's a lot more options that come with air handling units. So in terms of advantages, they usually have the most flexibility in terms of heat recovery, construction materials, installations. They can be installed indoors and outdoors. There's a variety of cooling options available that I previously mentioned. They've integrated operating modes. They're typically the most precise in terms of discharge air temperature and humidity control. They likely are the lowest energy usage, but they're also likely the highest installed cost, and many require skilled service personnel, and they'll often they're paired with chilled water systems, which bring their own set of unique advantages and drawbacks as well. So in terms of common chilled water system configurations, there are a handful of considerations that need to be made. Analyze the daytime and nighttime chilled water and heating water loads, because in a chilled water system, there's an opportunity to do some heat recovery. Do you want to use air-cooled chillers or water-cooled chillers? Typically, water-cooled chillers provide more heat recovery options, but are more complicated because they require a different heat rejection devices. In some climates, the use of a water-side economizer makes a lot of sense because cold water can be produced. But there's an interesting trade-off, because if you're using a water-side economizer to make the chilled water that you need for dehumidification, then you need to find another source for your hot water in order to do your reheat. And so there's an interesting analysis that can be done. And then there are alternate piping and distribution configurations. So in this example, there are 2 cooling only chillers on the left-hand side and 1 heat recovery chiller heater. All the chillers are controlled to make 40-degree chilled water with a 16-degree delta T. The cooling only chiller rejects their heat to the cooling towers, while the chiller heater rejects its heat to the heating water load. And so that load requires 105-degree water. And because these units are installed in a parallel configuration, all the units are loaded to equal cooling percentages. The heat recovery chiller, or the chiller heater, is sized for the heating load, while the cooling only chillers are sized for the balance of the cooling load that's not offset by the heat recovery chiller. At part load, there's a reduced return water temperature, meaning that the heat recovery chiller can't make its design heating water and cooling capacity. And so this means that an auxiliary heating device like a boiler or an air-cooled heat pump may need to be added to supplement the heating load. And there may be times when the chiller heater is producing too much heat for the heating system. In this case, the excess heat can be rejected through the cooling tower through the use of a plate and frame heat exchanger. This allows some of the heat to be transferred to the other condenser water loop while maintaining a separate loop for heating water. Some manufacturers also offer chillers that have additional condensers. So this chiller, while you can't see it in the picture, would have 2 condensers. Sometimes it's called a double bundle. So this allows the heat to be rejected to the cooling towers or the heating load. And it also allows the plate and frame heat exchanger that you saw in the previous slide to be removed. So this is a pretty common parallel configuration. There's an alternate configuration where the chiller heaters are preferentially loaded. A preferentially loaded heat recovery chiller would move the bypass. You can see that in my drawing that the bypass line, which is a gray pipe in these drawings, actually moved from the previous position. So this means that the chiller heater is now on the load side, which allows it to receive warmer return chilled water. This reduces the overall lift of the chiller heater so it can operate more efficiently. The heat recovery chiller, the chiller heater, is still controlled to make the system chilled water temperature. Another configuration, in the last one that I'm going to show you, is a side stream configuration where the chiller heater is installed in a side stream location. So conceptually, the side stream configuration makes things a little bit more simple and more efficient. The chiller heater is now controlled to maintain the hot water temperature. So the condenser water leaving temperature is now the set point for the chiller instead of a chilled water set point. So this results in the chilled water temperature fluctuating as the chiller heater operates. So the chiller heater only ends up pre-cooling the return chilled water before being cooled to the design leaving chilled water temperature by the cooling only chillers, the ones on the left. Because the chiller heater is used to serve the heating load, the fixed plate heat exchanger that I showed you before could also be removed. It's still in this picture though, because a lot of designers still like to install it for backup purposes. So if you look at a summary of those 3 configurations, parallel, preferential, and side stream, in terms of how we look at it as the side stream being the best configuration because it has the simplest system controls and it has the best system compressor power reduction. But there is a caveat, and the caveat is that the cooling only chillers, those are the chillers that were on the left side of the screen, their pumps will need to be sized a little bit larger. But that's about the only negative in our estimation. And so I'm almost out of time. We're almost at the top of the hour. And this is my last slide that I'm prepared to share with you. I will stay on for a little bit longer to answer questions if there are any. But where can I learn more? Ashrae has a lot of publications that can help you. Ashrae has a technical committee, a TC 2.2, Plant and Animal Environment. And this technical committee meets at the winter and annual meetings, and they are responsible for 2 handbook chapters. One of them is on growing, And you can see in the title of the technical committee, they also deal with animals, livestock. So there's a chapter on growing and livestock, and there's another chapter on drying produce and crops. Ashrae also recently created a new multidisciplinary task group, or an MTG, on indoor agriculture. It's called mtg.cea for Controlled Environment Agriculture. An MTG is a type of meeting where experts from multiple technical committees gather to do additional work. So you can imagine that there's a representative from TC 2.2 that comes to this MTG meeting. The MTG is brand new. They have met once at the previous meeting, the winter meeting, and there were a lot of people in attendance from a lot of different technical committees and a lot of other organizations. There's a hunger for more information and help from an HVAC perspective. And so this MTG has a lot of work to do to help us out. Joe Listerberg, you might be familiar with his columns in the Ashrae Journal. He is a prolific writer, and I think he's pretty witty and funny, especially in person. He wrote a great column in the June 2018 Ashrae Journal called "This Bud's for You." It's only a couple pages long, but he talked about a lot of the things that I talked about today about loads and how this is a dehumidification load because of the plants. And so it's a great article that spells it out in a somewhat humorous and witty way. And this is Ashrae, and a lot of what I've been talking about is related to dehumidification. And Ashrae knows a lot about dehumidification. We have a lot of great resources on that subject. They just don't happen to say plants or agriculture on them, but it's still applicable. There's also another organization called Asabi, which is a agricultural engineering organization. Asabi is partnering with Ashrae to create a document called X653. That's the project. It's called Heating, Ventilating, and Air Conditioning for Indoor Plant Environments Without Sunlight. This document is not published yet. It's in its draft phase. Earlier this year, they went through an equivalent to an Ashrae advisory public review. And so that's been done, and the group is meeting in order to take comments that were received and respond and refine their document accordingly. So I would expect this Asabi publication to be published later this year. And so with that, thank you for your time and attention today. And I'll stay on for some additional questions if there are any. Thank you. Okay, well, it doesn't sound like there are any additional questions. So thanks for your time and attention. Have a great day.
Yeah, hey, thanks a lot for presenting, Eric.
Yes, thank you, Eric. Appreciate your time. Yes, Tom. There will be this recording, and we'll end up publishing it on our website, and so we can send out information on that future.